We have four circular wheels, like, there are some, wheels, and each of them has the numbers from 0 to 9. So it is like, I think everyone knows the concept. So we have a, let me change the thickness of this. So we have a wheel, and we have 1, 2, 0, 3, 4, 5, 6, 7, 8, and 9. And we can rotate it. We can rotate into, the clockwise and, counterclockwise. It means that we can, have a transition from 9 to 0 or 0 to 9. So, but we have four of these guys. We have four wheels, okay? And initially, and actually four of them, makes a lock for us, and we wanna unlock or open the lock, right? And initially, all of them are, the 0. And we have some dead ends, meaning that if we, for example, if dead end is, let's say 1, 1, 0, 0, if we have this combination, we will be unable to open it. It will be locked forever. So it means that we have some dead ends, and we should avoid them, okay? And we have a target. For example, in the first example, you can see here, 0, 2, 0, 2. We want to reach this target starting with 0, 0, 0. And the question is, what is the minimum total number of turns that we can do to open the lock? And if it is not possible, we have to return -1. I want to go through the first example and solve, manually this problem, and then we will go to understand the details of the problem. First of all, you have to understand the problem really perfect to avoid any misconceptions, which is one of the really the mistakes of all of the interviewees. They don't, understand. You need to spend 3 or 4 minutes to understand, completely the question, even if you think you've seen this before. Please focus on that and check all the assumptions and what is the objective, what is your, the given, the assumptions, and then dive in, to find which pattern can be mapped to this problem, and then, go to the your solution. So let's say it is, like a dead end. Okay, let's say I want to solve the first example. The initial wheel is 0, 0, 0, and my target is 0, 2, 0, 2, and I have to be aware of all of the dead ends. So first of all, I want to make this guy 2. I want to make this guy 2. So I can rotate this one time. It will be 0, 1, 0, 0, 0. And it is not dead end. And in the second step, I want to make this 2. Okay, I did say second step. And right now, I want to go to the last digits. I want to make this 2, but if I make it 1, what would be happened? 0, 2, 0, 1 is dead end. I cannot do that. One solution is to go over 9 in the, let's say the reverse direction, 9, 8, and, go back to the 2. But if I do that, I will have, 8 steps to make this 0, 2, 0, 2. That's why I prefer to change, for example, this guy or the first one, and then change this to the 1 and 2. I want to go and write the 0, 2, 1, 0. And now 0 to 1, we don't have 0 to 1 in the dead ends. So now I can change this to 2, and then I will change 1 to 0 in the last step. So I will write 0, 1, 0 to 1, 1, 0 to 1, 2, and in the last step, I will make it 0, and it's done. How many steps I did? 1, 2, 3, 4, 5, and 6. And 6 actually is the optimal, the minimum total number of turns. So based on examples, if you, solve some examples, you will find some ideas how to approach the problem. And let's say go to the next example, example 2. For example 2, so actually it was example 1. I want to go over example 2. Example 2, we have 0, 0, 0, and the target is 0, 0, 0, 9. And we have only one dead end, which is 8, 8, 8. So how can I do that? If I rotate the last one in the reverse, reverse direction, I can make it 9, right? So it means that I can do this in only one step. So 1 will be the answer of this, the last example 2. Let's go and do the example 3. Target is 8, 8, 8, 8. So let's say I want to write again my 0, 0, 0, my initial value. And look at the dead ends. We have 8, 8, 8, 7, 9. As you can see, for first digit, I'm going based on the bits location. This is the first digit, right? 7 and 9. As you can see, for the third, the second digit, we have also 7 and 9. For the third one, we have 7 and 9, and all of the others are 8. And for the first one, for the fourth one, we have 7 and 9. And before diving into this, to solve this problem, whenever, let's say I want to make this 8. I want to make this 8, right? And assume all of the others are already 8. And I want to make this 8. The previous value of this can be 7 or 9, right? Depending on which direction we are approaching 8. And as you can see, for this guy, we have 7 and 9. Both of them are dead ends. So it means that I cannot make it 8. It is impossible. I cannot make it 8 by having all of the others 8. In the same way, for the other, like also we have same scenario. We have 7 and 9, 7 and 9, 7 and 9. It means that we cannot make it. We cannot reach to target because all of the, both directions are dead end for all digits. So that's why we will return -1 for this, because we don't have any answer. And for example 4, we are starting with 0, 0, and the target is 8, 8, 8, 8. But 0, 0, 0 is dead end. It means that initial value, initial state is dead end, and we cannot reach to targets. So similar to the example 3, we will return -1. Okay, that's the examples, and it is really important in the interviews have some examples, like 0, 0, 0, or the edge case examples. They can help you to understand the details of the question, the problem. So now it's time to detect which pattern we can use for this problem. As you can see, we have an initial point, especially for the people who join some previous patterns. I think they have the answer right now. Do you have any comments, you guys? before I dive to the map, the best pattern, I want to have your feedback. Any comment, any feedback? That's which pattern will be the best?
Backtracking.
Backtracking. You mean you want to use, when you talk about backtracking, it means you want to use DFS, right? Or recursive.
Mm-hmm.
So, okay, this is one of the, DFS and backtracking. Any other comment?
Probably BFS.
BFS. Okay. And any other comments? Okay. Actually, in most of problems, we approach to these exactly to these two patterns, and selecting which one is the best is really sometimes it is critical. And actually, before diving into the solution, I can say that for this problem we can use both of them, but one of them is much more better. One of them is better and easier to implement also, and even execution time of the one of them is much more efficient. And now we want to detect which one is better. Let's go and review the the problem. And for the problem, in order to find which pattern is the best, distinguish between these two guys, you have to focus on the the objective of the problem. What is the objective? Minimum total number of turns. Minimum number of the steps we are turning, right? When we have this kind of the minimum or shortest path, if you remember one of the meetups we had, finding the shortest path from the source to from the source to target, source to destination. And we had a binary grid. Let me write here. We had a binary grid, if you remember. And this is really the famous problem. We have, let's say, some ones, some zeros, and let's say we have source and destination. We want to let's say these guys are 0, 0, 0. We want to find the shortest path from source to destination. Ones are the cells that we are allowed to enter these cells, and zeros are some we cannot enter these cells. And the question is find the shortest path. And this was one of the basic problems that I taught in the BFS pattern. When we I want to review again. Actually, here you have an initial state. Let's say it is your source, and destination is your target. The destination is your target, which is, for example, 0, 2, 0, 2. And the objective is finding the minimum total number of turns. Actually, here in the basic problem we solved for BFS pattern, turns or moves are defined based on the problem assumptions. Let's say we have right and down, up and left, or we can have any kind of movements. If you remember, we had the knight chess, a knight piece in chess, and we have different. If we have here, we can go to this or we can go to this, right? And we can have different movements. And here also in the same way, we have some movements, right? Let's say I have 0, 0, 0, 0. How many possible values I have for the next state? I can change 0 in 2 ways, right? The first one, I can make it 1 or 9. So it can be 1 or 9. Let's say I want to do only 1 turn. I want to know if I do only 1 turn, how many different next states I will have. And I can do this in the same way for the second one, will be 0, 1, 0, 0, 0, 9, 0, 0. As you can see, for each of these guys, we have 2 possible movements, and 2 for this, 2 for this, and 2 for this, right? And it means that we have 8 movements. In a similar way, in the shortest path, we had, you know, depending on the problem definition, let's say we are here, we can have 4 movements. Or we can have, if we have also diagonal movement, we can have 8 movements, right? As you can see, we can map this problem exactly to the shortest path in a binary grid. But the nature of the movements is not like, you know, going to the right or left. The nature of movements is changing every digit in 2 directions. And we have 8 neighbors. Do you remember we said for each node we have 4 neighbors or 8 neighbors? Or if we have only the, let's say we have movements to right and down, we will have 2 movements. And in this case, we have 8 movements. And you can map this problem exactly to the BFS pattern and find the shortest path, which will be minimum total number of turns in this problem. Why we don't use DFS? What is the difference? Because we can implement exactly this logic using the recursive function or depth first search. Do you have any idea, any comments? I strongly recommend to solve this using the BFS, but you can solve using the DFS. But do you have any idea why we prefer to use the DFS or recursive solution?
DFS is used to find a path from S to T, while BFS is used to find the shortest path in the graph, assuming the edges are either of the same length or or unweighted, either unweighted or same length. BFS gives you the shortest path between S and between the source and the destination. Exactly.
Perfect. Actually, when we go depth first, it means that we go, you know, all of the paths we have, you know, to depth, we have to try all of them. At the end, we have to find which one is the minimum. Okay, it means that we have to, for all cases, for all inputs, we have to try all paths. But in BFS, we don't do that. We go level by level, and when we reach to the destination, it's done. We don't need to try all of them. We don't go in depth of the grid. And that's why when you see the shortest path, if it is not a weighted path, I mean that turns or steps are not weighted. If you don't have any weight for your steps, definitely BFS is the best one. But if you have weighted, let's say some movements have some, you know, different weights, you have to use DFS or backtracking because you need to try all of them. And formulating the DFS, if you have weighted path, is much more easier than implementing the BFS. But if you have binary grids, or, you know, like here, you know, all of our movements have same weights. We don't have any weight for our movements. So, and you have the optimization problem. It means, you know, finding a minimum or maximum. Dive into BFS. But you should be, I really, you know, I want to emphasize this because it is the mistake of, you know, lots of, you know, people, my students, that when they say the shortest path, they dive in, you know, to BFS. But if it is weighted path, you have to use DFS and backtracking. You shouldn't go. You can implement by BFS, but it will take more energy and more time. And if I want to map the grids for this problem, for the people who are, you know, this problem is a little new for them, I want to do map this problem to the shortest path in a grid. Let's say we have a grid and all possible values for our wheels are inside of this, okay? So how many, you know, how many wheels we have? 1, 2, 3, 4. And we know that for every of them, you know, we have 10 possible values for this. 10 possible value, 10 and 10. So how many combination we will have? 10 power 4. So let's say I want to put all of these values inside of a grid or matrix. And I will put, you know, 2 first digits here and 2 first digits here. It means that I will have 100 row and 100 columns, right? Only I want to, you know, graphically show how it is related to how you can map this to shortest path problem in a grid. And let's say, you know, this is the initial value, which is 0, 0, and target is somewhere, you know, like I want to go to the random, you know, let's say 0, 2, 0, 2. And this is our target. And all of the other ways, some of them are dead ends. And we know the dead ends. Like, you know, zeros in, you know, the shortest path problem. They are, we are avoided to, we shouldn't, you know, enter these guys. And we start from, you know, this cell and go to the next level. And next level, how we identify, we have 8 neighbors. And we know neighbors, how we calculate the neighbors. They are, it is not as easy as, you know, them, you know, moving in a grid. Okay, so I will calculate, we will write a neighbors function to extract, to calculate all the neighbors of, you know, each node, each cell, and we will go forward until we will reach the targets. It is, but we will have really some random, you know, movements here. I don't know how they will be handled, right? So we will have some random movements. And that's the nature of the problem, you know, and we have really good keys in the problem, which is really important, is the minimum total number of turns. It should trigger you toward the BFS, but review again. If you don't have any weight for your each step, use the BFS without any doubt. Any question about mapping the problem to the pattern, BFS pattern? And BFS pattern actually is for grid here. Actually, we don't want to make, you know, create a grid, but it is logically there, right? We don't want to create this guy, any matrix, but we know that it is kind of having a grid. And as you can see, let me go back to the patterns. This is the last pattern, BFS in graphs and grids. This is the last pattern, and we map this problem to the last pattern. And if you know, if you already saw the BFS pattern, you know which data structures we need to implement a BFS inside of the graph. I want to talk about it in this slide. So we know that for BFS we need a key, right? I don't want to. I assume you guys, most of you guys know the basics of the BFS. That's why I don't want to waste more time in this part. But if you have any question, please ask. I would be really happy to explain the basics, even if you have any question. Let's go in, you know. Okay. For the BFS, we know that the key data structure we use is a queue. Queue is first in, first out in a data structure. It means that I want to put 0, 0, 0 inside of the queue, and I will pop it from the queue let's say this is my queue. I will push in the queue, and I will pop it, and I will push all of the neighbors. I will add all of the neighbors. This is the the general concept of the BFS. We have a queue. We start with the first element. Here is the wheels. We will add here, and in a while queue, inside of a while queue loop, until queue is empty, I will pop it and I will add all of the neighbors. But here we have some constraints. For example, we have dead ends. So it means that I need to be aware of the dead ends, right? If it is dead end, I shouldn't add the inside of the queue. So we have to check the neighbors. If they are not inside of the dead end, our dead ends, I will add inside of the queue, okay? It means that we don't add always 8 neighbors. We have 8 potential neighbors, but some of them are dead ends, maybe. And we have to check them. Also, we need to calculate something, which is the number of turns. And in the BFS, for each level, when I add the other guys, I can embed a variable nearby my, my input to specify the number of turns. I want to carry my objective inside of my queue. This is the easiest way. Sometimes there are some other solutions, but I don't want to make it, difficult. So 0, 0, 0. The first one, the initial value for my turns will be 0, right? So that's why I will, add the first one will be 0 and 0. And 0 is number of turns. When I go and add the next one, all of the next neighbors, I will make this 1, 1, and 1. And I will go forward. And finally, whenever I see in my while loop, whenever I see the value of my wheels is equal to targets, I will return the number of turns because I already carried all of the steps. And that's the whole idea. But you have to be fluent in using doing the basic BFS. And right now I want to go and write a code for this part, and I will explain more also in the code after I'm writing. Let's connect my keyboard. Any questions so far? Perfect. So let's go to the text mode. And I'm going to go in the styles should be code. This guy. And let's go and start, the implementing. And first of all, we said, we need, queue, and we know that queue. I didn't talk about why we are using queue. I will talk about it, inside of the code for the people who are not, who don't know, the basics, the basic, concepts. So I need to import DQ, which is double linked lists, because in order to have the queue, we use double linked lists, which is a DQ inside in Python. And the reason we are using, as you can see here, for queue, we want to add always at the end of this data structure. And also we want to remove or pop from the beginning. If I use a simple array, adding at the end will be done with order of 1, but removing from the beginning, you can do that, but it will be done with order of n, which is size of your array. Because if you move it or pop it, all of them will be shifted. And The shifting will be order of n. So array is not good because we want to have order of constant for pushing and popping from our data structure. We don't want to cost any time complexity because of using a data structure. And maybe you want to use, let's say, a linked list, simple or singly linked list. In the singly linked list, adding at the end will be done. It is exactly the opposite of the array. Adding at the end will be done with order of n, because you have only head pointer. You have to traverse whole linked list and add at the end. But removing from the beginning will done with order of 1. But if we use double linked list, we have head and tail. We have both benefits. We can add at the end because we have tail pointer with order of constant, and also we can remove from the beginning with order of constants. That's why we use the queue. I saw some people say I can remove. We have some functions, built-in functions in the array to remove from the beginning. Yes, we have, but the problem is the time complexity of that operation is order of n. You have to be aware of the built-in functions you are using. If you are using a built-in function, it doesn't mean the order of that function is constant. Okay, the implementation of that function, you can see the for loop to shift all of them. Okay, so that's why we use the DQ, which is a double linked list. And let's go and define my function, which is I'm writing the open like. And for open like, we have dead ends and also targets. We have two inputs, dead ends and target, and we know that the default, the initial value is 0, 0, 0, and we don't want to have that guy as inputs. So, first of all, we said we need a queue, right? I want to define my queue, which is a DQ. I want to put the initial value. I said initial value should be the 0, 0, right? And also we want to put the number of turns as initial value. So that's why I want to put a tuple inside of this. Actually, I want to add a, let's say, I want to add a, let's say, a tuple of, let's define this as an empty queue, and then I want to append at the end. I want to make it more readable for everyone. I will append a tuple, and the tuple will be 0, 0, 0, 0, and 0. Okay, this is my initial. We put this guy inside of our the queue. And the reason I'm doing that the tuple, because we just want to read this and we don't want to change it. Okay, we want to read this and we will increase this guy and we will add a new tuple. That's why we don't need to use any the lists, but it doesn't matter. You can use even the array. It's not the issue. And also, as I said, we need to search inside the dead ends, right? Dead ends is a list right now, or it is a simple array, right? And always we want to search if the neighbors are inside of this. If I keep dead ends as a list, the searching or finding time complexity will be order of n, right? But if we convert this to a set, hash set, and we know that the searching, the time complexity of doing the finding inside of the set is order of constant, and it will help us in terms of the time complexity. That's why I want to write dead set as set of dead ends. Right? This is only for decreasing the searching time complexity to order of constants. As you can see so far, we use queue and hash sets data structures for this problem, right? And also, when we have grid or graph, and we are using BFS or DFS, we need to use visited or seen sets, right? Or seen or set or array, because if we, let's say I reach to the cell of 0, 0, 1, 0, I don't want to repeat this, right? When I see this guy as my neighbors, I have to avoid it, because if I don't check that, I will have an infinite loop, and my algorithm will not be stopped. It will run forever. So that's why we need a set named scene, and the initial value is 0, 0, 0. And in Python, you know that if you use the brace, you have the sets. Okay, so far, we have also a scene set, and so far 0, 0, 0 is our scene. Why we use sets for scene? Because we want to search inside of that. That's why the best way is to use set, and the searching will be done with order of constants. So these are our
quick question.
Yeah.
So you can have a same set for both dead ends and scene, right?
Dead end and you mean we can use one variable for
One
both
set.
of them?
Yeah, one set probably.
But dead ends are constant. We don't want to change them, right? Dead end is our inputs. Some cells are, some combinations are dead ends, right? And we don't want to change it. It is constants. But scene will be, we will add, every cell we are seeing, we will add inside of the scene sets. And
right.
they are not dead ends, right? The definition of these two guys are, different.
True, but when you append, before appending to the queue, you basically check if it's seen or if it's in the dead end, and then append to the queue, right?
Yeah, actually, yeah, you can do that, because let's say we can say all of the scenes are dead ends. Yes, exactly. You can do that. Yeah, because after we see, it is like kind of dead ends. But the problem is we have another constraint. The problem that we have to. Yes, yeah, it is working. Yeah, you can use exactly.
Okay.
You can use, but in terms of, in order to make it more clean here, I think more readable. But you can do that. Yeah, exactly.
Okay.
Because when we see when we see a specific combination, we can say that this is dead end, because I shouldn't go inside of it. Yeah, that's true. Thanks for the comment. So let's go ahead and write our while queue. While queue, it means while queue has something inside. We have something inside of the queue. So what is the first step? Popping from the queue. And I know that inside of the queue, we have two. For each item inside of the queue, we have two items. One of them is wheels. Wheels is exactly, the string with, 4 digits. And also we have turn count. We have two variables, and pop left. Actually, I didn't write in the queue. That's pop left. Let me increase the length of this guy. Okay, so we pop this. This is the first thing we have to do. But before, and the next item is we want to add the neighbors. But before doing the neighbors, we have to check maybe the wheels is our, the destination or our targets. So that's why I have to check if wheels is equal to target. So we found, we have reached to the destination, and I will return turn count. And also, if this guy, the wheels is dead end, is inside of the set, I shouldn't continue, because it is dead end and I don't need to find its neighbors, right? This is another case I have to check. If wheels in dead sets. If it is inside of the dead set, means it is, one of the dead ends, continue, right? We don't need to find its neighbors. Go ahead and, pop the next elements because it is dead end. And for all BFS algorithms, we have this kind of, first we do the pop left, we do some, kind of checkings, and then we will say I want to go and find all the neighbors of this guy. Let's say I have a function that calculates the neighbors. Even the interviews, in the interviews, don't dive in those functions. Assume that you have that. Based on that function, implement your main algorithm, and then go ahead and implement all of the functions you have used. I'm assuming that I have some let's say neighbors. I have a function named find neighbors, and I will write it in the next step. And the input is wheels. Actually, inside of this function, we want to find all 8 neighbors. Find all 8 neighbors. Okay, we want to find all 8 neighbors. We will write this. But it is really good, approaching the coding interviews. Assume all the functions and go ahead and develop all of your, algorithm. It shows that you can think top down, and it is really you can captivate your interviewer. So let's say we have this, and then I want to go and do I want to do the for neighbors and add all of them inside of the queue. If we didn't see, if we already didn't see them, right? So I will write for neighbor in neighbors. We already calculated this guy. For neighbor and neighbors, I have to check if neighbor is not in scene, right? If neighbor not in scene. If it is in scene, I don't need to add it because we already saw this. So I will go and add this inside of the scene, add neighbor. And we add this, in the scene, first of all, and also we need to add this in the queue, which is the important part. But if you don't add this inside of the scene, you will have infinite loop. You have to add this. If you forget this line, you will have infinite loop. And the last step is queue that's append. And please, be aware of, the functions. For hash sets, we have add and remove, but queue is append. You have to be fluent in these guys in the interviews because it will save your time. You don't need to struggle what was the function for queue or the set. For the important data structures and the language you are working with, you have to know all of them without any doubts. So I will add here the neighbor, right? The neighbor we calculated inside of this find neighbors, and this is a list of strings. We have 8 strings inside of this neighbors, and the neighbor is one of them. So I will add this, and also we know the previous value for turn counts, and the neighbor will be +1 because we are assuming that we churned. The neighbor means we churned one of the wheels, right? So I will add turn count +1. And after we do all of these guys, and the while loop is finished, we will return. Actually, if we find a target, we return the turn count, right? Let's say we do all combinations in the while loop, and we didn't return. It means that we don't have valid answer, and we will return -1. And this is the whole algorithm for this problem. And I think it is pretty straightforward for the people who know the BFS. But detecting the pattern is a little challenging, especially detecting, distinguishing between, the BFS and BFS. Let's go and talk a little about, how we did this. So as you can see, always, actually, I forgot to write the find neighbors. I will write this also, the find neighbors function. But as you can see, we have a queue, and we need usually some helper data structures, like, some sets usually, and we have a while queue. The first operation is pop left, and then we will find the neighbors, and we will add all the neighbors. And these guys are like, the base cases in our, the recursive, functions. And if we implement this algorithm using the DFS, we will put these guys in the base case of our recursive call. But I think it's not, for this kind of problems, it's better to use the BFS. Any question about the algorithm? And if you don't have any question, I want to go and write it, find neighbors.
Hey, Wahid, quick question on, so if you could have checked the neighbors inside headset, right? So then we could have avoided the second if condition, right?
Which one, this one, the second one, right?
Yeah.
Okay, so can you repeat your question? Can you repeat your question? Sorry.
So while adding the neighbors to the queue, if we are checking if it's inside the dead set, then there's no need for that if condition, right?
Yes, exactly. Yeah. Yeah, exactly. This is one of the, for example, here, in the neighbors, if we check if it is not inside of the dead end, we don't need this if statement. Yes, exactly. Because, we are adding all of these guys. I think it is better, thanks. I think it is better, I like that. Let me go to the text mode. I think it is better because we don't need to push and pop, we can decrease the number of, push and pops. Thanks for the comments. Actually, we can guarantee that. But, we are assuming the 0, 0, 0 is not in the dead sets. Yeah, we are assuming with this assumption, we can, raise this, or we need to check in the beginning. That's if it is in dead end, return -1. But I can, raise these guys and do this here. I think that it is much more, usually I use that logic, but right now I didn't do that. If neighbor is not in scene, let me change this. And neighbor not in dead sets. So actually we are not adding any dead end inside of the queue. So we don't need to check that. But if we do this, we need to also check the first item, because 0, 0 also can be added inside of the dead end, right? And I can do this here. Let's say if let's say 0, 0, 0, after sets, right? I will check that here. If 0, 0, 0, 0 in that set, so it means that the initial point is, that is dead end. So I will return -1. So if we can, change the code in this way, yeah. And I think it's not a bad idea. It's really good because we can check here. We don't have to push and pop, all the dead ends inside of the our queue. It will increase, the number of push and pops, but it doesn't change the big O. Both of them are true. Okay, so let's go and write, any question, any comment? Okay, let me, I just wanted to show this, this part that, based on, your comment, but I wanna return to the original solution. It is a little shorter, but definitely we can do that one. Actually, I don't have the control Z more. I will put both of them actually in the notes. Both in that set. Okay. Okay, so let's go and write the find neighbors. Define and define neighbors. We know that how to. Let me write inside of this text box. Okay. We want to find neighbors, and we have, let's say, I want to write a note or wheels. Actually, we wrote here the wheels. Actually, let's get it to write the wheels. Okay, we have the wheels, and we want to return a list of neighbors. I want to find the results as a list, empty list. So we have 4 digits, right? I need a for loop, which is my I is, when I'm writing I, let me write the index. For index in range 4. Okay, I want to go one by one. And for each of them, I have to do 2 operations. But before that, we know that the wheels is a string. And I want to increase this by 1 or decrease by 1, right? So I have to convert that digits. Let's say I'm starting with, let's say I have, let's write here, 0, 0, 0, 0. I want to convert this to 0 to 1 or 9. I have to extract this and convert to the integer. I want to convert it to the integer. So that's why let's go and do this here. So I will do the, let's say, wheels of actually the index. I have this. I want to cast this to the int. Input inside of, let's say, it is my x. So right now I have 0 in x and it is integer. And now I want to increase or decrease this by 1, right? So I will do for all of them. So I have 2 deltas, right? I want to add +1 or -1. That's why I want to do for in d, which is, delta, in I will have -1 or 1. This is really, really, beautiful way to add this. I can do this, without doing the for loop, but I like the, putting the deltas inside of the tuple, and then, we can do this inside of for loop. So I want to change x to y. I have 2 options. I can decrease by 1 or, increase by 1. Because I put, d can be -1 and 1, I can add x plus d. But I have to do modulo 10, right? Let's say if I have 0, +1 will be 1, modulo 10 is 10, but -1 will be -1. And we don't have -1, right? But -1 modulo 10, -1 modulo 10 is equal to 9, right? That's why, if we do the modulo 10, we will have, both directions answer. So let's go and go to the text mode. Okay, so for d in this, I will do the y is equal to x plus d modulo 10. Okay, and now I have y, and I need to concat all of the strings before index, and then put y in between, and all of the strings after index, right? I can do this here. Let's say I want to do the I want to write the result that append. I want to add the new one. What will be the new one? I will do the reals from the beginning to index, right? From the beginning to the index, index is not inclusive. It means that all of the characters, all of the digits before index, plus a string of y. I have to cast my y to the, because y is an integer. And also I have to go from the index plus 1 to the end. I will write reals index plus 1 to the end. Let me raise these guys. Okay, I need to, because I saw some people are struggling with the math here. Let me type this guy here. Let's say -1 modulo 10 is equal to 9. That's why we use the modulo for even, no, sorry, -1, I mean, yeah, 0 minus 1 will be this guy, will be, then can I change only this font? Yeah, okay. Okay, so that's why it is working for both directions. And at the end, we will return result. As you can see here, we calculate 4 items here and 2 combinations here. We will have 8 new values, which are all neighbors of the current reals, or the next possible values for the reals. And we have the find neighbors here, and this is the whole code. And that's it. Any question? And if you don't have any question, we can go and calculate the time complexity and space complexity for this problem. Any comment, any question? Okay. So let's go. What is the time complexity? I think most of you guys know what is the time complexity here. In the worst case, how many times you will have loop inside of this queue?
10 raised to 4.
Yes, n to the 4, right?
Yeah.
Yes, exactly. And because we say that n. Let me draw mode.
But here it's dependent both on the number of wheels as well as the number that the wheels can take, right?
Exactly. Yeah, we can generalize. We can generalize that the time complexity, but we can start with the, let's say the simplest one, time complexity, and we know that the total number of the combination is 10 to the 4, right? And we assuming that the 10 is the number of digits. This is number of digits, because we can have some wheels that we have only 0 to 4, for example. Okay, and actually number of digits, or I can name this as number of, yeah, and the 4 is number of wheels. So if I put the number of digits as D and number of wheels as N, we can write D to the N, and we can generalize our let's say time complexity, right? But what is the power of BFS? Although it is 10 power 4, especially if we don't have any answer, like the example 3. For example 3, BFS and DFS, both of them will go 10 to the power 4, right? Even BFS should try all of them at the end. Q will be empty, and Q will be empty, and then we will return -1. But if we have something like this, let's say the first example, we have only 6 steps, right? DFS or recursive should try all the paths. Exactly, again, we will have 10 to the 4, 10 power 4. But BFS will find only in 6 loops in the while, right? So that's why this is the power of the BFS. Actually, you can say that, let's say the number of the turns, let's say the T or K is the number of, actually, let me make that better name. This is the minimum number of turns for our answer. We can say that, for BFS, we can write here our, the time complexity as K, which is the number of turns. But we cannot say the big O is this, right? Big O, because we have to consider the worst case. The worst case for BFS is when we don't have any answer. We will try all of them. But if you ignore, if you ignore, that special case that we don't have any answer, BFS order will be order of K, which is the number of turns. But is it true? Let's say we have, the order of D power N. Order of K is, if we consider the minimum number of turns as input. Actually, it is not, it's not, let's say, usually in big O, we write our big O based on the inputs, not output. But it is really important to discuss in the interview that actually the big O is order of K for all the cases that we have answer, for all the cases that the answer is not -1. But for the -1, definitely is D power N. But it is not accurate. How can I accurate this guy? It is not correct. Look at the code and find, where we do some, we know that the number of the, how many times we do the while loop, it is D power N in the worst case. But let's check if we do any extra operations inside of this or not. Any comments? We need to multiply this guy with something because we do some calculations inside of this while loop that it's not order 1. Any comment? Any question? I don't want to dive in the solution actually. I prefer to. Any comment? Go ahead.
Multiply with 8.
8, yes. As you can see here, we do the for loop, right? In order to find the neighbors at each round, we do for here, right? And also, so we have order. Let's talk about it. Here for, and also we do the 2 for loops here, right? Which is 8. And what is 8? 8 is exactly the order of, the number of wheels, right? So we have order of 2n, which is equal to order of n, right? Equivalent to order of n, right? And also we do some concatenating here. When you want to concat and make your string, it doesn't cross order of 1, right? You have 4 characters and you want to concat them. This operation, it is not the order of constants in concatenating. We do order of n also, or n divided by 2, which is, actually if n is number of wheels, actually it is, order of n, right? So order of n we have also here for concatenating. So it means that the time complexity of this guy is order of n squared, and you have to be really, really aware of all of the built-in functions like this, and you have to be sure that it costs you more than order of 1 or not. And we have order of n here, we have order of 2n or order of n, and because they are nested, so the cost of defining the neighbors is order of n squared. And we know that how many times we have the loop, which is d power n, so you will have n squared times d squared. And also here we will have n squared times k. Okay, any question for time complexity? This is the one of the really mistakes that most the people are doing. They ignore all the built-in functions or built-in operations like this, the concatenating. You have to check the time complexity of all of these guys. So if you don't have any question, let's go and write also the space complexity and finish this problem. So what is the space complexity? Any comment?
10 to the power of 4.
Order of? Order of n, or I didn't get your answer.
Oh, I said 10 to the power of 4.
It will be order of n.
Order of n. Okay. So which data structures we used? We used the queue, right? So let me write here. We use the queue. We used two sets, like in a scene, and also dead set. Okay, these are the data structures we used. So what is the length of the queue in the worst case? We add all the combinations inside of the queue, right? In the worst case, it will be d power n, right? And then I say, one of you guys, said, 10 power 4 for here. Yeah, it is true. And scene also, we go and, scene also can be d power n in the worst case. A dead set actually is, constants. I don't need to, add this because it is the inputs, right? Mm-hmm. Do you have any question?
Yeah. So Q at any point will at max have all the neighbors of the current element, right?
Yes.
So how can it? So it will be all, and the current element is like find neighbors, so which is order of n. So Q should also be order of n, right?
You mean, we because we are popping, the length cannot be 10 to the power 4, right? 10 power 4.
Yeah.
So but let's find some example. You can find some examples that you are adding all of them. Let me think about it, to find really the worst case. Let me write the answer, and then we can find a worst case example that we add all of them.
Okay.
Let's say, but actually you are true, it's not exactly d to n, but it cannot be n also, because it is accumulating. Well, let me give you the example. If we have 0, right, and we will have 8 guys here, right?
Right.
And then we will pop this guy, and we will have, actually we pop this, and I will pop this guy, and I will add another 8.
Okay.
It is increasing, right? And you can do some calculation. It is not exactly d power n, but the order is d power n. And it was really good, good comments. But if you calculate this, it will be maybe d power n divided by some constants, right? But the big O will be again the d power n.
Okay.
Okay, but actually we can handle that. We can decrease the space complexity. Let's say I'm doing this. So the next round I want to pop all of these guys, but again I will pop add all the neighbors of the eight guys,
So
right?
even if you're adding, like, let's say you pop 0, 0, 0, and then you pop the first element from the first 8 neighbors, and then you add all of its 8 neighbors. The number 8 is proportional to n, right? It's not proportional to d.
And actually, let me check the number of digits. Yeah, it is dependent of, yeah. But you know, the size of let me. But you know, if you do some calculations for this part, it is accumulated, right? And the number of, you know, because you know, we know that the whole the number of, you know, total combination is d power n, right? I'm sure that if we do calculations, it will be some constant of this. If you see only the 1 or 2, the second step, you see that only 8 is, you know, that has impact, right? But how many 8s we have, it depends on d. Does it make sense?
Oh, okay.
Yeah, how many of 8s we are adding, especially in the last steps, we will have lots of 8s. And how many 8s we have, it is d.
Oh, okay.
Okay.
How many 8s we have is...
So assume, you know, let's say assume, you know, you have only 2 wheels, right? You will have 100, right? Only you will have 100, you know, combinations. And you will have only two digits, you know. You definitely, you will have less. You cannot say that it depends on only you know, the 8, or we are talking about it doesn't depend only on the d, which is the the n, which is here, it is, you know, 4, right? Yeah, here, which is 8, and let me, yeah, I think, you know, the 8, which is the function of n, definitely we see, you know, the impact of this, and how many times we have this, it is, you know, depending on d. And we can do some calculations. It's like, you know, the series we are writing, it will be some, you know, kind of series, and at the end you will see that it is a, you know, the some, you know, you will have a constant as a coefficient for d power n. Okay. Yeah. So any other comments? It was really good comment, and actually we can do this as a maybe I will do this, you know, for the next session. I will show you how it is. It will be exactly there. The big O will be d power n. Okay.
So I have a question about the wheels. I was wondering if instead of storing that as a string, you stored it as a list of 4 integers, or a list of n integers, actually, then wouldn't you be able to avoid the need to do the concatenation in the find neighbors function? Because you would just have a list of 4 of n numbers, and you would just increment or decrement, you know, one of those numbers.
Yeah, actually, if we convert it to the list, right, you are true, we can avoid this concatenating, right? But we cannot avoid this guy, right? You know, these 2 for loops, because we need to have a 4, you know, we need to do the 8 operations, right? And the first order of n, you know, it will not be avoided, but, you know, concatenating, I think, will be, yes, it can be avoided. Yes. You know, before starting, we can, you know, change this to convert this to the, you know, the array of integers, and at the end we can, you know, convert this. Really good comment. We can decrease this to order of n times d power n. If we convert this guy to the list, I think it is, you know, it should be true, if I'm not missing some really important points. Because if we have an array, I'll say we have an array, and we will increase or decrease that. That's it. Yeah, definitely. Thanks for the comment. It was really nice, and we can decrease this to n D power n. Any other comment? Okay, actually, I don't know. We will have time to. I think I can do that. The next question. This question is considered as a medium level in Leetcode, but actually, this is medium. It is not even for medium questions. We have, let's say, for medium questions, some of them are so close to easy. Some of them are so close to hard questions. This is the medium to hard question, and it is frequently, this kind of questions are are really frequently asked in the the top tier companies. That's why I've selected this guy, and this is really good. I like the scenario of this this problem. It is like kind of the real problem, and it gives me a really good feeling that I'm solving some scenarios that give us really good feeling, and they are practical in terms of the scenario. Any question? If you don't have, I will go to the next problem. I will go really fast to finish it in in 10 or 15 minutes. I don't want to go really. I don't want to explain so much, and to be able to solve the other one. So the next problem is the merging the case sorted lists. Actually, the problem, this kind of problems, you don't need to think about, which pattern you have to use, because they are pretty clear, completely clear which pattern you have to use.